Hi everybody, it's my pleasure to welcome you to this second session of POPL on program logics. So today we have in this session we have three great talks. The first one is going to be BiSikkel by Joris Ceulemans.
Yes, thank you. So let's see, I mean, what's better to digest our lunch than talking about modalities in type theory? So let's do this. Right, so if we have a type theory, well, we typically prove its soundness by constructing a model of the type theory. And the most famous one is a set model, where we just interpret types as sets. But there are plenty of others. For example, we have the topos of trees, we have cubical sets, etc., etc. Now, as a general notion of model, we will take a category of families, or a CWF, but it's not really important to know what that is in this presentation. But let's say there's just a general notion of a model of type theory. So we could have several models of type theory, and then we have interesting functors or morphisms between them. For example, we can consider the later functor on the topos of trees. Now, an interesting question is, how can we internalize these morphisms? So how can we, in other words, extend a type theory with constructors that will eventually be interpreted as these morphisms? And it's exactly that kind of type constructors that we will call modalities in this presentation. So why would we be interested in this in the first place? Well, such modalities can extend the expressivity of a type theory. More concretely, via modality, we can express certain aspects of the behavior of a function in the type of that function. So for example, we could, using a modality, express that a certain function is parametric or that it's irrelevant, or we could use a modality to express the recursive behavior of a function, and then we get to guarded recursive type theory. Now, in the literature, there's a lot of work on how to add modalities to type theory, but most of these papers, they consider a single application, and then they consider just the modalities that are necessary for that application. And in order to unify many of these systems, Daniel Gratzer and co-authors, they developed what they call Multimode Type Theory, or MTT, which is a general framework for modal type theory parameterized by a mode theory. And so the mode theory captures the entire modal situation. And so it consists, among others, of a set of modes. And these modes will, in the model, correspond to these different CWFs. And it also consists of modalities, which will then correspond to the morphisms between these models. And if we then instantiate MTT by a concrete mode theory, then we get an entire modal type theory that can then be used to program and prove with a certain modal application in mind. Okay, but if we really want to work in MTT, if we really want to write programs and proofs in it, we need an implementation. And at first sight, there are two possible approaches for obtaining an implementation of MTT. Either we could extend an existing proof assistant and add support for modalities to it. The advantage of this is that such an existing proof assistant already has a user base, already has some interesting features that we can use to write programs. But on the other hand, we are extending the proof assistant, so it could in fact be that we end up with a system that is unsound. Then, as a second approach, we could also just start from scratch and develop an entirely new proof assistant. The advantage of that is that, well, we get something that is very suitable for programming in MTT, but of course there is then no existing ecosystem. And there has been work in these two directions already, so that has been, there has been work on this. But actually, and what I want to talk about in this talk, is a third alternative approach, and that's based on the idea that type theory can eat type theory. So we can use type theory to formalize type theory. And then the question is, of course, can we also use type theory to formalize MTT? Because if that's the case, then our approach could also be to write a library for MTT in an existing proof assistant. And so that could have some nice benefits. For example, we would be working in an off-the-shelf proof assistant already, and soundness would be by construction because we are actually just implementing a library in an existing proof assistant. We're not extending a proof assistant. And then the third point is this library approach allows us to kind of modularly use modalities. So what do I mean by that? Suppose that we are working on some, for example, Agda project, So no modalities involved at this point. And then at some point, we discovered that we need guarded recursion to write a certain function. We would then instantiate our library with a mode theory for guarded recursion, and then we could use the primitives for guarded recursion to write our function, and then we would somehow hope that we can extract this function to get a normal Agda function that we can then use further on in the project. And then if at some later point we discover that we need, for example, parametricity to prove some property, we can instantiate our library with a mode theory for parametricity, use the primitives there, and also extract the proof to get a normal Agda proof. So we actually, with this library approach, we only use our library when we need the modalities, and for the other parts, we just use normal Agda. So the question is, of course, can this be done? And so a couple of years ago, we gave a positive answer to that question for a simply typed fragment of MTT. So there we implemented our Sikkel library in Agda. And so Sikkel consists of, well, 3 layers. So the first layer is a syntactic layer, and that is a formalization or an encoding in Agda of what we call Multimode Simple Type Theory, so, or MSTT. So that's a simply typed fragment of MTT. We can instantiate that with a mode theory and then write modal programs in it. Now, Sikkel also consists of a type checker, and the type checker is sound by construction, which means that whenever it decides that a program is well typed, it will also output the denotation of that program in the semantic layer. That semantic layer is a formalization of presheaf models in Agda. And then we have this extraction mechanism that I told you about. So that allows us to extract the denotation of some programs to ordinary Agda functions, and I will specify a little bit more details about that later in the talk. Okay, so that's all nice, I think. So now we can write modal programs in our library in Agda. But of course, well, we are at POPL. We saw yesterday in the business meeting that verification and proof assistance are popular topics here. So we do not only want to write programs, we also want to prove properties of our programs. And unfortunately, with simple types, that's not possible. And so therefore, in this work, we present BiSikkel, which adds a logical framework, a multimode logical framework called MuLF on top of Sikkel. And this multimode logical framework can be used to reason about MSTT programs. We also provide a soundness proof and a proof extraction mechanism, which I will talk about later. And by implementing this, we also made some major reworks on Sikkel, so most notably on the MSTT representation and program extraction, but that's also something for later. Right, so let's make this a little bit more concrete by considering a particular application of modal type theory, namely guarded recursion. So here we have an Agda function that takes a function f from a to a value a, and produces a stream of a's, namely the stream a, f of a, f of f of a, etc. And how can we implement this? Well, we could implement it as follows. So we say the first element of that stream is a, and then the tail is obtained by mapping f over a recursive application of iterate fa. And if you try to write this in Agda, then Agda's productivity checker will complain and say, well, this definition is not productive. But actually, if you stare at this for a little bit, well, I don't have the time to do that right now, but if you stare at this a little bit, you see that this definition actually is productive. So Agda's productivity checker is wrong. Now, how can we solve that? That is, well, one possibility to solve this problem is using guarded recursion. So guarded recursion adds a later modality to our type theory, which is a unary type constructor. And then we can see that, well, we can construct a type of guarded streams, and a guarded stream of A's has a head of type A and a tail of type later guarded stream of A. And also, the final thing that guarded recursion adds is a fixed point operation called loop induction. So in order to produce a value of type x, we need to produce a function from later x to x. And this later will make sure that every fixed point, well, every definition is productive. And using these primitives, we can then, we can then use our library to write this iterate program. So that's what it looks like in the syntactic layer of BiSikkel. I will not spell out the details, but you can see what it looks like in BiSikkel. Now, actually, we could also implement this iterate operation in a different way. we could also just say, we get this iterate prime here, that the head is again A, but the tail is iterate prime of F and F of A. So now we have two algorithms that should compute the same stream. Can we actually, well, prove that they compute the same stream? Well, we can start by taking iterate FA, expanding its definition, and then, well, it's a pretty, well, we can show a lemma that mapping F over iterate FA is, will get us to iterate F of A. I will not show that proof here. And then we would hope to apply an induction hypothesis. So then we could say, okay, now we're in the tail, and in the tail, iterate is equivalent to iterate prime. And then we're just back at the definition of iterate prime. So that was not too hard, but of course the question is, can this reasoning be made sound? Is this indeed something we can do? Especially this induction hypothesis. And so an intuition for why we can use this induction hypothesis here is because, well, the tail of a guarded stream appears under a later modality. We've seen that via loop induction, constructing a value of type X, we can assume something of type later X. And so indeed, well, if we have some variant of loop induction for proofs, we would be able to do this. But that means that we need to apply later to propositions. And so that really means that we need a multi-mode logical framework to reason about MSTT programs. So what does that then look like? Let's take a little look at what MuLF looks like and how it's implemented in Agda. So here we see that there are two Agda data types, one of propositions and one of proofs. The idea is that MuLF is a subset of MTT. So we can see these propositions as actually dependent MTT types, but they are only allowed to depend on program terms. So actually we have a stratification of MTT into a simply typed fragment and then a dependently typed fragment where we only have types that depend on the simply typed terms. And so here we see then that this bprop for BiSikkel proposition is indexed by a context that can just contain program variables. And we see that there are constructors, for example, to express that two MSTT programs are equal or to apply a modality. We also have our data type of proofs, which is also indexed by a context, for example, for providing reflexivity proofs. Now, in this way, it's possible to write invalid proofs. And so BiSikkel also has a proof checker, which comes in the form of an Agda function check proof. It takes a proof context. Proof context can contain not only program variables, but also proof variables, so assumptions. It then takes a proof, where we just, well, this 2ctx function, it just removes all the proof variables from our context, and it takes a proposition, and will then tell us whether P is indeed a valid proof of phi. Not only that, but when it decides that indeed this is a valid proof, it will give us the denotation, well, it will give us some evidence of that fact by constructing a semantic term in the presheaf model of type the interpretation of phi. So indeed, this proof checker is sound by construction. Now, to implement this, we need some more infrastructure. Well, we need to expand and modify some of Sikkel's infrastructure. First of all, we have an intrinsically typed representation of MSTT terms. So here we see that the terms are indexed by a context and a type, which means that it's actually impossible to write terms that are not well typed. We also expanded the presheaf formalization layer of Sikkel. We proved many new coherence laws. We implemented a fueled normalization algorithm, which is also sound. So when it does not only return a normalized term, but also a proof that the denotation of that normalized term is equivalent to the denotation of the original term. And we also implemented a substitution algorithm that we described earlier, and we proved that it's sound with respect to the presheaf model. Okay, and then the entire proof looks like this. I will not go into all the details, of course, but I want to note that the first few lines are the proposition we actually want to prove. Then the majority of the slide here is the actual proof. That seems like a lot of code, but actually we can see that these are just the four equality steps that we saw in a previous slide. And then the last two lines, the fact that those type check means that running our proof checker on this proof is actually successful. Okay, let me tell you a little bit about this extraction mechanism. So recall from the first slide that we have these models of type theory, and one of these models is the set model. And so that means that in our and so recall that all of these CWFs correspond to modes. And so suppose now that we have one mode that gets interpreted as the set model. That means that types at this mode are interpreted in our formalization as just Agda types, and terms are interpreted as normal Agda programs. And that means that such programs are very easy to extract to an Agda program because their denotation already is an Agda program. And so that's the idea of the extraction. Extraction is only possible from this trivial mode. And what happens if we have a program at a different mode? Well, the idea is that you then first need to apply a modality to get to that trivial mode. We reworked the internals of this mechanism with respect to Sikkel. So this mechanism was already there for in Sikkel for programs. We reworked the internals, and we also added a proof extraction mechanism. So that allows you to extract proofs. Now you get normal Agda proofs about extracted MSTT programs. Unfortunately, due to type checking performance, that doesn't work for this iterate example, but we have shown it to work for more trivial examples. Okay, finally, something about the design choices of our library. So first of all, we have intrinsically typed programs. So recall, we made MSTT intrinsically typed, but extrinsically typed proofs. Intrinsically typed proofs would mean that we encode all the proof rules in the data type of proofs. So that we cannot write invalid proofs, but we have seen that we need a proof checker. So in BiSikkel, you can write invalid proofs. We've tried to come up with an intrinsically typed encoding of proofs, but unfortunately, that makes it, performance issues then occur when we try to write actual proofs. A second design choice is that MuLF, our logical framework, is a strict subset of MTT, and that allows us to reason in a modal setting without having the complications of interpreting type theory in type theory. Why complications? Well, basically you have two options. Either you could use intrinsic types, but then it becomes very hard to write programs, or you could depend on extrinsic types, but then it becomes very hard to state the Agda type of the type checker if you want soundness by construction. And so to wrap up, I presented BiSikkel, which allows multimode reasoning as an Agda library. It works with arbitrary mode theories. There is also another example in the paper. We have moderate use of modalities, sound proof checking, sound program, and proof extraction. And there's also some future work, but I'm told to wrap up. So thank you for your attention.
So we have time for a few questions. Perfect.
Hi, Max New, University of Michigan. Considering these performance issues, to what extent do you think that they could be addressed in the implementation, or that they really need to be changes to Agda itself to address these performance issues?
I think so. I'm not really aware of what the source, like the real source of these performance issues is. But I assume that you would need to rework Agda in some way to resolve them, or try to work out this library idea in another proof assistant. So yeah.
Because I find this idea of embedding a logic, domain-specific logic, is something you see all the time at POPL. We develop the domain-specific logic. We want to get out the actual semantics, basically like what Iris does, right? Generalized, right? But we need to figure out what are the actual features we need and performance we need from Agda to be able to do this more effectively.
Yeah, agree. Yeah.
Hi, I'm Anthony from University of Illinois. Thinking about this proof extraction to set, I'm wondering, from a theoretical basis, what are the obstructions to extracting to a different mode? Something a little more complicated than set.
I think there's not. So that would mean that you get like a different presheaf category. So there would not be like theoretical obstructions, other than I think the obstructions would be more practical. So I think what's very nice here is that you really have to use the modalities to go to the trivial mode. So everything happens at the syntactic level. But of course, if you're more familiar with how the presheaf semantics works internally, you could actually like leverage that. But the point here is that for the application that we studied, you could just use the modalities for that, and you don't actually need to bother. Yes.
Okay, let's thank the speaker again.